Welcome to this video. In this one, I'll show you how to solve problem 5 of the sample final. We're given a connected undirected weighted graph G. Define the cost of the spanning tree to be the maximum weight among the weights associated with the edges of the spanning tree. Design an efficient algorithm to find the spanning tree of G, which maximize the cost above. Okay, well, I guess to understand the question clearly, you need to write the actual cost. So let me write that down. So the cost is basically a function of any tree given to it. So the domain of this function is the set of all spanning trees of G, okay? And the cost then will be defined to be what? The max among all edges. So E in capital E. But this is only edges of the tree, of course. So ET, and then write the weight of E. Okay, so this is exactly the cost. All right, so if we're given a graph, something like this, okay, let's call this one A, this is B, this is C, and we have a bunch of things like -1, 2, and let's say this is 1. Then, what are the set of all spanning trees of this one? So this is a graph, G, okay? So the set of all spanning trees, well, we only have, it would be basically 3 of them, okay? So if we call the set of all spanning trees to be tall, then let's draw the spanning trees. We have something like this one, A, and then C, -1, 2. There's one over here. Another spanning tree would be one rooted at B. Okay, so this goes to A, goes to C, and AB is -1, and BC is 1, and then there's another one rooted at C. Okay, and so AB is, or AC is going to be 2, and CB is going to be 1. Okay. So given this tall, what we need to do is search for the tree that maximizes. See? We want to maximize this cost. So let's actually compute this cost for all these trees in here. Okay, so what is the cost? It's simply the weight of the maximum edge weight. So here we have -1 and 2, so the max is 2. Here the max is 1. Here the max is 2. So then clearly we have 2 solutions. We have this is a solution and this is a solution. So we need an algorithm that finds at least just one of these solutions. It doesn't really say which particular solution, just one solution that satisfies this. We need to maximize this one. And if you recall, we have one algorithm that can solve this, which is Kruskal, but we have to actually turn this into a maximum spanning tree problem. But then we don't really need to do this. That would be a bit inefficient. There is a more efficient way to do this, which would be as follows. The idea is that we only need the maximum edge, right? So here's the idea. Search through all edges in E and find the maximum edge. Oops. Edge E and E. So the idea is like you do a linear search, okay? And so once you've found this edge, then all you need to do is include it and then do a DFS tree. A DFS tree can be done in linear time as well. So Okay, so then what we have to say is do a DFS tree starting at the, so basically, okay, if this maximum edge, actually let's call it UV, okay, starting at U, okay, so we do a DFS tree starting at U. In this case, what happens is that UV will be included. It has to be included. That's just how the algorithm works for DFS tree. Okay, so it iterates over all adjacent vertices of V, and it's going to of U, sorry, and it's going to include UV, and from V would include other vertices. But I suppose we have to make a constraint here, is that when this is represented, this should be the very first one represented in the list. What do I mean? I mean, like, when you have the adjacency list, you need to have something like this, UV, so that we ensure that UV is there, because maybe at some point we have something like this one, X, and then XV. So then what happens is that when you do your DFS tree, XV will be an edge, but then UX will not be edge because X has already been included. Sorry, I mean UV will not be an edge. Okay, so we will basically not be able to have that. So this is just one constraint that we need to do. Okay, do a DFS starting at tree or at U. So you have to mention that constraint somewhere in the algorithm, but this is just a rough sketch of the solution, okay? So you search through all edges in E and find the maximum edge UV, and then do a DFS tree starting at U, okay? We need to ensure the edge UV is included in the tree. This means we may need to change the representation of the graph such that V is the first vertex adjacent to U. Okay, so basically then the running time is big O E plus B, which is definitely more efficient. What am I doing here? So this, yeah, yeah. This is more efficient than having Kruskal, because with Kruskal it would be this, right? But you have to multiply this by log V, which is more work. So this is the most efficient one. So if you do Kruskal maximum spanning tree, that would, at least according to Jang, he said he would take off like 3 marks from it. I'm like, that's dumb, but anyway, this is the best one that you can do, and this is at least his algorithm. Okay, hopefully this was helpful.